Hi everyone. So in the previous video, we said that scientists figured out that if we take light from a distant star, that light from the star is going through the gas of that star before entering the Earth. And we can use a spectroscope to split that light up, and we'll see black lines that refer to the type of gas that that star has, because the gas from the star will absorb the different wavelengths of light or certain wavelengths of light, creating a pattern of black lines depending on which gas that star has. Now, we also notice that if we compare a laboratory reference of, say, hydrogen, we'll see that in our lab that it has a certain that it has certain black lines and certain spots. This is the identity of hydrogen in our electromagnetic spectrum. But if we compare that same hydrogen, light passing through the hydrogen in a nearby star or galaxy or a distant galaxy, we see the same pattern of the lines for hydrogen, but we're seeing these lines moving more towards the red side of the spectrum. And here's why. Well, we already said, according to the Big Bang Theory, the universe is expanding. And if the universe is expanding like the balloon, then the wavelength of light coming from the beginning of the universe must have also expanded with it. And we know that with increasing wavelength, we might get a different type of light. And with decreasing wavelength, we might get a different type of light. So, say the light from the beginning of the universe, the Big Bang, came from the Big Bang, right? And it started approaching us, the Earth, a long, long time ago. And it took a while to approach us, right? So by the time that light reached us, the universe has already expanded, kind of like this balloon. That means by the time that light reached us, that wavelength of light must have also expanded. So say, let's now talk about a star. A star from long, long, long time ago, from the beginning of the universe. And that star has a gas, and the light passed through the gas of that star and then entered the Earth. And then from our lab, we split that light into different components, and we found that the gas of that star absorbed this particular wavelength of light, green, and formed this black line. And we have this laboratory reference of that particular gas with all these black lines, right? But um, since by the time that light reached us, the Earth, the wavelength of that light expanded, which means that even though it should look like this, the black line should be here and all the other components should look like this, by the time it reached us, that particular light, all the wavelengths of each individual components of this rainbow also increased, meaning the red wavelength increased to maybe infrared, the orange wavelength increased to maybe red, the yellow wavelength increased to orange, the blue wavelength increased to green, and the purple wavelength increased to blue, and so on. And that means all of this shifted more towards the red side with increasing wavelength, right? But we can't all really see this on the spectrum because it's a rainbow. We don't really see the shift, but we can see the shift in this black line where the gas absorbed the wavelength of light. So, where in this case it was supposed to be green, we have a black line. If everything else in this spectrum of rainbow is shifting towards the red side, the wavelengths are increasing, this black line will also shift with it more towards the red side. And it will look kind of like this. That's why, as we're seeing farther away into the universe, we're seeing that the same black lines. Um, for this particular gas is shifting towards the red side more and more, because the farther away something is, the longer it will take for that light to reach us, and the longer it will have time for the universe to expand. The universe expanded, right? That means the wavelength of that light slowly increased by the time it got to us, and that's why the black lines look more towards the red side. And this is our first evidence, which is the red shift of light. This is what we call it. And we're seeing that as we're looking farther out into the universe, the same exact element with the same exact fingerprint looks like it's shifted towards the red side. The light going through that gas before it reaches us, because that spectrum moves to the red side, because the universe has expanded since then. This is called the redshift of light, and it proves that the universe is not only expanding, but everything around us, like galaxies and stars, are also moving away from us, because the wavelength of everything is increasing. And even though it should look a certain way compared to our lab evidence of a certain element, it doesn't, because all the lines are shifting towards the red as the universe is expanding. Let's write this down. An evidence of the Big Bang Theory is redshift of light, where all objects in the celestial in the universe are starting to move away from us because the wavelength of light is getting longer as the universe is expanding. So, if we're comparing the electromagnetic spectrum of an element, say hydrogen, that same element's electromagnetic spectrum coming from a receding galaxy, meaning a galaxy moving away from us, will look like it's shifting more towards the red because the wavelength of light is expanding. Now, say something was the universe was contracting, it was getting smaller and smaller from here to here, then my light wavelength would decrease, right, from here to here. And if the light wavelength decreased, then all my black lines would start shifting towards the blue side because because it shows decreasing wavelength. So even though from my lab, this element spectral line should look something like this. This is the fingerprint. If we're looking at a farther star, such as the Barnard star, and if that star is moving closer to us because the universe is getting smaller and smaller, then those lines would move towards the blue side because all these wavelengths would slowly shrink or decrease, causing the black line to move towards the blue. We call this blue shift. So, blue shift of light, if that was the case, then the wavelength of the light would become shorter since the universe began, and the movement would be closer. Those elements, all the universe, the stars, the galaxies in the universe would start coming closer to us. If compared to our lab, the lines are moving towards the blue side. And if compared to our lab, the lines of an element are moving towards the red side, it tells us that that particular thing is moving away from us. So, how come the farther we look out into the universe, the more the lines are shifting towards the red? That's because the farther away a celestial object is from us, the faster it's actually moving away from us. And that's what we're seeing here. The farther away something is from us, the faster it's moving away as the universe is expanding. And that's it.